Should we start then?
Yes, I'll introduce you now. Welcome everyone to the Topos Colloquium. We're very excited to welcome Pierre-Louis Curien, with affiliations there on the slides, talking about new approach to optopic shapes. Pierre-Louis, whenever you're ready.
Okay. Okay, so can I start now?
Yes, go ahead.
Okay, great. So, this I'm happy to talk in this context, and this talk is dedicated to my friend and colleague Marek Zawadowski, who unfortunately passed away last year. And well, the talk is very much related to some of his work. And this is also joint work with a student, master student of mine, Louise Leclerc. Okay, so in the talk, I will try to motivate Opetopes and of course, introduce them in some way by means of pictures which I'd like to call featuring the geometry of unbiased associativity. And I will try to explain with the pictures. And then once these objects will be motivated, the talk will go more technical. There are different presentations of these objects, and the goal of the talk different combinatorial presentations, and the goal of the talk is to relate them. Okay, and there is a positive case, well, where Epitopes are positive to one, so they represent operations with at least one input, but several inputs in general, but at least one, and to one output only. That's typical of Opetopes. And the general case is when the inputs may be zero, so then it's only many to one. Okay, so that's part 3. Part 3 will be very short because, well, I will be short of time anyway. Okay, so geometry of unbiased associativity. So I hope these pictures will be somehow self-explanatory. Suppose that I'm in this situation, I'm given a number of functions that are composable, like shown here on the right of the picture, f, g, h. And well, I can be clever enough, that's the word unbiased in the title. I can be clever enough to be able to compose them in one shot. Okay, so then that's what is written on the right. F composed with J with H just in one step. But but I could also want to compose G and H first. Okay, that now we're looking on the left of the picture, and the result, which is then G composed with H, with F. Okay, and you see that this is shown geometrically as gluing together two shapes. One shape that features the composition of G and H, and the second shape that features the rest of the composition. And here we already have, in this picture, we already have 0 Opetopes, 1 Opetopes, 2 Opetopes, and 3 Opetopes. So the whole picture is a 3 Opetope. It has one target, which is the figure on the left, on the right, sorry, which is a 2 Opetope. And on the left, you see that it has 2 sources. We call them sources. The 3 Opetope has 2 sources, which are the 2 triangles there, glued in some way. Okay, and we can continue on. And you see, well, that I give a name to this 3 Opetope, which is AS for associativity. Okay, which is, of course, it's a kind of unbiased associativity. Okay, good. Now let's go to 4 Opetopes. So this picture is somehow a coherence cell. So let me try to explain it. So you have the blue, the yellow, and the green part. All of them are 3 Opetopes. And now I'm building a 4 Opetope, which I called Co, which is, of course, referring to a coherence property. And this 4 Opetope has 1 target, okay? And the target explains that, well, to compose F, G, H, and K, I decided to compose first H and K, then with G, and then with F. And the yellow one in the middle is somehow quicker, is a faster guy who said, no, 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 I don't need to decompose the composition of G, H, K. I can do it in one shot, but I still need to compose with F. So that's the story told by the yellow thing, okay? And the blue thing is actually glued in one of the sources of the yellow thing and says, okay, in a second stage, so you have to think things in layers or in stages. So the first layer is, so to say, is the yellow thing, okay? Where I already did some decomposition of the sequence F, G, H, K, but gluing the blue thing inside the yellow thing says, oh, okay, I further decide that actually I didn't quite know how to compose G and H and K directly. I actually needed first to compose H with K and then with G. Okay, so you have this kind of delayed decisions on how to compose things. And well, I don't have too much time to detail the picture, but you have to think that this picture really is a coherence property because it relates, well, categorically, you would have the picture that is drawn below. It's essentially the same picture, and then this picture should convince you that it's like in monoidal categories, except that we are, so it's a diagram with different associativities and it commutes. Okay, so that's a coherence condition, but it's written in an unbiased style, so it's not a pentagon. But you could do the exercise actually of making a subdivision of the pentagon with triangles like this, and you would recover the pentagon, but I don't have time to do that. Okay, so this is some kind of motivation that Opetopes are shapes for refining decompositions of sequences of compositions, something like that. And then also Opetopes can be good in inserting identities. Okay, so after all, we want to describe some form of higher categories. So we do not deal only with composition, but also with identities. And then we have, for example, this picture is a picture of 3 Opetopes. Well, I omitted to write down the target of these 3 Opetopes. So these are only the 2 sources of 3 Opetopes. And you see that the identity here, so you have to read again this picture as saying, well, I want to compose, well, it features the fact that F can be composed with the identity, and the way to represent the identity is with a 2 cell that has no input, but only one target, no source and only one target, the thing called I or iota on the small round thing at the right of the picture, okay? And this is called degenerate 2 Opetope. Okay, so maybe you can already have guessed that 2 Opetopes are in bijection with natural numbers. They actually represent operations with a number of inputs. So if, for example, in this picture, in the yellow picture here, we have the Opetope 3 because it has 3 inputs, the trapeze, the trapeze on top of the yellow thing has three sides and a target. So it's an operation with three inputs and one output. And the one below is with two inputs. And there are also ones with one input only. And this one here was with zero input. Okay, so far the motivations. So now we want to describe those shapes. Okay, so the origin of those shapes come from a work from Baez and Dolan. It's already quite old, maybe 40 years ago or something like that, maybe a bit less. And they have been studied in various contexts by different people. And in particular, they have been revisited by a group of people, Kock-Joyal-Batanin-Mascari, Mascari. And they tried to understand Baez-Dolan construction, and they came up with a combinatorial description, which is very nice, which is called zoom complexes. So in this diagram, the Baez-Dolan thing is the historical first appearance. Then the zoom complex side of this triangle was also known from, let's say, I don't know when, but later, but also is already classical. And then the two other things called, with this funny name, epiphytes and dendritic phase complexes. This is a formulation of the same objects, but with different points of view, which I worked out with Louise Leclerc. And well, part of the goal of the talk is to present these different versions of Opetopes and to relate them to zoom complexes. But of course, I also will have to introduce zoom complexes. And the interesting thing is that one of those, so the ones called dendritic phase complexes, are very nicely related to the work of Marek Zawadowski. And Louise has shown so she has written 3 drafts, and one of her drafts is actually now published and makes the connection very precise between the setting of what we call here dendritic phase complexes and Zawadowski's setting, which is principal positive opetopic cardinals. So we are not going to go into Zawadowski's work, but you can see this picture at least before entering into details as one outcome of this work was to relate Zawadowski's combinatorial approach with the approach of zoom complexes and also the approach of Baez-Dolan. So the idea of the whole work was to connect different lines of work with quite different formalists. Okay. So now let's start with, okay, and no, last thing I want to say is that there are 2 versions, an easy one and a more difficult one. So, well, relatively easy one, which is a positive case where we do not accept diagrams like this, okay? So we don't have these looping, these one cells which are loops. We don't have them. Well, actually, we don't have loops in any dimension. We do not accept loops. This makes life slightly easier. So that's what is written green in these diagrams. And the general case. So as you see, some arrows in this diagram are in dashed lines, which means still work in progress. So some of the work presented here is clear in our works in the positive case, and is not yet entirely clear in the general case. Okay, good. So let's work on the positive case. And so I will start with the zoom complexes. And I will go with pictures. Okay, so now I will try to explain more formally this game that I explained of doing compositions in stages. So first of all, we can represent the right of the diagram here, I called it the target, okay? We can represent it as a tree, okay, of, well, you know, this composition can be seen as a tree. Well, you have F5, above F5 you have F4, above F4 you have F3, because the output of F4 goes into the input of F5, etc. So you can represent the sources of the target, which are F5 to F1 in a tree form, okay? And then this discourse that I had, I can represent it in forms of circles around this black tree. So when I said, for example, that alpha 1, okay, is a composition of just F4. Well, I said it for another diagram, but it's exactly the same story. So how to read the diagram on the left? Well, I compose F4, F3, and F2. And you see that I actually do a circle around F4, F3, and F2 to make this clear. And then the whole thing is composed with F1. That is what alpha do is doing on the left. So you see that my second circle now encloses F1. And the last circle is the final composition with F5. And this is my last circle. Okay, and now it is, well, it is quite easy and quite known, I think, that such circlings will produce a tree. You can see these circlings as a tree where all the circles become nodes of the tree that is written on the left. So the tree on the left records roughly the same information. And you see that the tree on the left, well, records the circling in the form, in the form of the tree, and that the nodes that were nodes on the black tree on the right side become actually leaves on the tree on the left side, okay? So there's a slogan here. If you do a circling of the nodes of some tree, well, you get, it's the same thing as to build another tree whose leaves are the nodes of the previous tree. Okay. So before going on, okay. So this is an example of a 4 Opetop. And we can play this game of circling to explain the whole picture, okay? But of course, it would be a bit time consuming to explain all the picture by details, but you can probably see that in this picture, so this is a 4 Opetop, and it has a target, which is, well, below the arrow omega, so the second sub-picture on the down this omega arrow. And then itself, it has a target, which is represented as TT omega, if you can see it. Maybe I zoom on it, so it's on the right of what I'm now zooming. Or I could use this. Maybe I can use this. Yes. So this whole thing here is the target. This thing here is the target of the target. And it's actually written T omega and then TT omega. And then this one cell here is the target of the target of the target. And this thing here, the 0 cell, is the 4th target of omega. So the idea of a zoom complex is to represent the successive targets from the lower dimension to the highest dimension. So, well, For example, you can see that, yes, I hope to hold everything in the same, yes, I hope you can see everything in the same screen, yes. So for example, this target here, this one here, yes, sorry, yes. This thing here is represented by this black tree here. And then the circling here that is represented here is already preparing the ground to understand this 3 Opetopes, okay? And hence, altogether, it's going to describe, at the next stage, it's going to describe the whole, the whole second part, this thing called T omega is going to be described here. And the circling, the red circling here, has become a tree structure, which is black. And the new circling is preparing the ground to understand the whole of the Opetope. So the whole of the Opetope is a tree, and we can try to read, well, let me try. We can try to read this tree, at least the beginning of it. So you can now just look at the sources of these 4 Opetopes. So the sources are in this purple color, and you have A1, A2, A3, A4. And it's not difficult to see that they have a tree structure. So you have A1 at the root, which receives A2. So you have A1 at the root, which receives A2 and A4, which are respectively here and here, and A2 itself receives A3 as indicated here, okay? And the sources, well, there's a notion of what are the inputs of A1? Well, the input of A1 are are B0 and B7. So A2 is plugged into the source B6 of A1, okay? A2 plugged in the source basis of A1, and base6 of A1, sorry, and you can see this information is exactly recorded here. A2, sorry, A2, yes, A1 receives on, what did I say? No, sorry, it's B6 and B7. My eyes are not good. So A1 has 2 inputs, B6 here and B7 here. And so A1 receives A2, A1 receives A2 on B6. Okay, so I cannot, of course, go into all the details, but I hope to give you the flavor that this sequence describes the targets and how the targets somehow fit together, okay? And the magic is that this description captures all the information of the picture above. So this can make a definition of Zoom complexes, of Opetopes, and they are known under the name of Zoom complexes. Okay, so now the second definition, it's the one that we call epiphytes. So this second definition, actually, well, it's very related to the previous one. So we also recognize and use the tree description of the sources. So here I have made the exercise. This is a 2-dimensional picture, okay? And so we can do the Poincaré dual of this picture, turning every 2 cells into 0 cells, turning every 1 cell in 1 cell, and turning 0 cells into 2 cells. Okay, that's what the Poincaré duality is about. So every triangle, well, every little 2 cell in this diagram becomes just a point or a node, and you see that you really get the true structure. So here you have that alpha 3 receives alpha 2 along F7, and alpha 2 receives alpha 1 along F6, and this is just a transcription of what you see in this picture. And okay, so we have these trees, but now instead of insisting on on recording targets, instead we try to understand sort of recursively or hereditarily. We try to record, so alpha 1, alpha 2, alpha 3 are themselves opetopes of the dimension of codimension 1. So here we are describing the 3 opetopes. So alpha 3, alpha 2, alpha 1 are themselves 2 opetopes, sorry. And those 2 opetopes are themselves described as trees. Okay, so you see that the idea is for these notions of epiphytes is to formalize opetopes as trees whose nodes are themselves decorated by trees. Okay, but these each time we decrease in dimension. Okay, and this is the reason why we call them epiphytes, because this is what what you find in nature. Okay, an epiphyte is a tree growing of a different sort, growing on a tree of a different sort. Okay, that's the definition of epiphytes. Okay, so now a little bit of formalism. What we mean by trees, of course, is what everyone thinks is a tree, but there are some special things that are very well known and common in the community of people who do operas. But maybe it's worth telling. So we are considering trees which has leaves. So that means edges that come out without having an end edge. So B5 and B4 and B5 and B1 are the leaves in this tree. And okay, and I have advocated in our joint work with Louise for the practicality of what we were doing. It was interesting to write the edges as being, well, so instead of having a set of nodes and a set of edges, we have a set of nodes, and each node has an arity, and the arity is actually the set of its incoming edges. So, for example, the arity of A1 is made of these B1, B2, and B3. And also, we have this kind of atomic description of trees, which is very convenient for what we are doing. We write edges in this form, and we call them triplet. So, for example, to describe this edge here, we say that we have a triplet saying that A1 receives A2 along B2. Okay, so you will see a lot of these notations in what follows. Okay, so I will skip a complete formal description of our setting for trees. I will just mention that in the positive case, we only manipulate trees that have at least one node. But we also, in the general case, there is also the case where a tree doesn't have any node, and then in this case, we call it improper, and it has only one edge, okay? And this edge has a name, okay? And we write it in like this, okay? And we call it an improper tree. Okay, and of course, I forgot to say that, well, it has to be a tree, so there should be no cycle. Okay, but of course, it's a tree. Everybody knows what a tree is. Okay, and some notation that will also be used. So for each node, we use this notation with this funny sign. Okay, it's the same sign I used for exactly here or here, okay, but now in the vertical direction. And this symbol is for, okay, it's overloaded in the sense that I use it for a node to describe its output edge, okay? And okay, so the output edge of A2 is B2. The output edge of A3 is B3. And the output edge of A1, okay, it has a special name, so we call it bottom of T. So it's a way to name it. So we have this notion of we call it down of. So down of A is just the output edge, and we also have down of an edge, and down of an edge is the node to which this edge goes. Okay, so down of B5 is A2, etc. Okay, so I hope it's clear. And down is not defined for bottom of T. Okay, so, and last thing I need for the sequel is I need a notation for recursively manipulating trees. So a tree whose root is A, okay, can be written in the form, in sort of a term, if you want. Its root, to which are grafted trees in some of the positions that are allowed by A. Allowed by A means that A has a certain arity, which is A of A, and on some of these incoming edges, I will attach other trees. And you see, because the trees have leaves, sometimes there is nothing attached. So for example, here, there's nothing attached. And it's precisely because it's a leaf. Okay, so I think it's enough for notation. And now I can risk the formal definition of positive epiphytes. So it's an inductive definition. A positive epiphyte is, in the dimension 0, there is only one such thing, and we have a notation for it, okay, this lozenge. And then starting from 1, it's an inductive definition. So we are given a proper tree, which we call omega. And for each node of omega, we are given an n-1 epiphyte. So we are now defining n epiphyte. Sorry, I should have written n epiphyte. So every node comes with an associated n-1 epiphyte, which we write like this: the source of omega at A. That has the property that the nodes of this, because being an epiphyte, it's itself a tree, so the nodes of this tree should be exactly the arity of A. And also, we have some condition on the triplets of this tree. Each time we have an edge in the tree, we have to respect this invariant that the B source of the A1 source of omega should be the target of the A2 source of omega. And let me illustrate this in one picture here. So this is the picture of 4 Opetopes which I gave before, and I want to show you some situations that would not be allowed, that are not allowed thanks to this condition. So for example, switching the roles of A4 and A2 here would not work, because A4 has a target which has the form of the triangle. Okay? It's a 2 Opetope which is actually a triangle, while it cannot fit into B6 because B6 has the shape of 2 Opetope with 3 inputs, so it cannot work. Well, it simply does not fit geometrically. So this is an explanation of this condition. And this condition is called inner, okay? Good. And then, well, the whole point of epiphytes is that there is no notion of target except in this condition, which means that the target is not part of the structure, so it has to be computed. So the distinctive feature of epiphytes is that target is a derived notion. And now I will try to explain how it is derived. And for those of you who know the story of Opetopes via polynomial monads and the plus construction of Kock-Joyal, etc., will recognize it, because essentially epiphytes try to be a combinatorial account of their very condensed definition, which is very nice categorically, but is difficult to, well, has to be spelled out to be manipulated combinatorially. And this is what epiphytes were meant to do. So, okay, so in order to compute targets, we have to understand the operation of substitution of trees inside nodes of another tree. So here I had tried to represent this operation. So of course, trees, well, people are quite familiar with grafting of trees. So you have a tree and then you have a leaf and you graft another tree on some leaf. Okay, but here we do something else. We do not graft on leaves. We do not graft. We substitute in nodes. So it's a quite different operation. And for example, here I have an example. So the idea is that we have this node A1, which is ternary. It has 3 inputs, B1, B2, B3. And I'm allowed to make a zoom on this node and to replace this node that is now large enough. There's a hole that is large enough so that I can plug in another tree in this node. And let me plug this tree, which of course opportunely has its leaves are named exactly like, are identical to the outcoming edges of A1. So then the operation of substituting is sort of evident. You just insert the tree, and B1 here goes to B1 here, and B2 here goes to B2, which means that the tree will continue there, and okay, and the same for B3. Okay, so the result here is given here. Okay, so there is now a technical description of the substituted tree, which I will not go into the details of, but just notice that, well, roughly speaking, the triplets, what I call the triplets, so these are, if you prefer, the internal edges of the resulting tree, either come from the first tree, okay, come from the first tree, or they come from the ones I substituted in, and some are new in the sense that, or are replacing other ones. So for example, B2 here, which used to connect A1 and A2, is now connecting it's now connecting A5 and A2, because B2 corresponds to this leaf of the substituted tree. So we need a little vocabulary to explain well how the edges of the new tree are formed. But again, I'm not going to enter into detail. So it's written here, but we will not detail that. Okay, so now that we have this notion of substitution in trees, there's a, well, sorry, once we have this description, we can now describe what the target is. So remember that our goal was to define the target of an Opetope. So we have this formula, this recursive formula, which again, for those who know about the work of Kock and others, is exactly what happens, written in syntactic terms. What happens in their work, translated in syntactic terms. So the target of omega is, if omega is written recursively, like, well, its root, and then a number of sub-opetopes omega b, then how do you obtain the target? By taking the source of omega at the root of omega, so the root is here. So you take the source at the root, and in this source, for each node B to which a sub-opetope omega B was attached in omega, you substitute the target of the sub-opetope omega B. Okay, so I will illustrate this in a picture, but let me give you a few informations about this. So first of all, what is the basis of this induction? Well, if the opetope has actually only, as a tree, has only one node, so we write this like this, okay? So it's an opetope that has only one node, no internal edge. Then the target is actually the source at this node. Well, it's actually the case where B is empty in this definition. So the base case is included in this synthetic description, but it's good to observe it, what the basis of the induction is. Okay, so the important thing is that, of course, we have a lot of things to check. So the first thing is that we did not define the target yet. We defined just a tree structure, but okay, we have to define an epiphyte structure. So we have to attach suitable epiphytes to the nodes of this target, okay, but we will do it next slide. But before that, for example, we need to check that this substitution is well defined. So we need to check that the leaves, because we substitute a tree for a node, so we have to be sure that the leaves of what we substitute are actually the arity of the node B, okay, which itself, by definition of opetopes, is the source at B of the source at the root of omega. So we have to check this, okay? Okay. So I will not detail it, but it can be checked in, well, by sequence of 3 equalities. But the point I want to make is that in order to check this, I need to have to use this equation, okay, which has to be proved, and it's a globularity equations about targets that I will explain next slide. So just to say that all this definition is extremely intricate, and everything has to be proved. The correctness of this definition has to be proved with a bunch of properties to be proved together by induction. So it's something that is rather delicate, but it works. Okay. So so now let's complete the description of an epiphyte. An epiphyte has sources that are given by this equation. Okay. So this is by definition. And then, and you can see it as a globularity condition, okay? Globularity in the globular world is something that tells you that the source of the target is the same thing as the source of the source. And here you see source of target is source of source, but of course you have to specify which sort, okay? So, and same for target of target is target of sort. So this is the other globularity condition. And this equation tells us that the target of an epiphyte is the same thing as the target of the source, the root source of omega. Okay, so it happens that okay, and this is a property, and it has to be proved together with all the rest of the good formation of the whole Opetope. I mean, it's a few pages of mutual inductions. Okay, so now I want to briefly mention that besides this inductive definition of target, there is a more algorithmic definition, which is quite useful, and that actually was proposed by my co-author, Louise. And I will not detail it because I want to keep a few minutes for the last part. But the idea is that we can characterize when we have a, so we know that the nodes of the target are the leaves of the Opetope. So we want to know when two leaves of the Opetope will be related by a triplet, so will be one above the other in the target. And it happens that this is entirely determined by all the tree information that we have in the different sources of omega. So each triplet like this in one source of omega will give rise to one triplet in the target. But I don't have time to go into details. Okay. Okay, so this was an example of computation of the target, but I think I see the time and I won't explain this. Okay, so okay, I won't explain this either. This is the epiphyte description of this example that we have seen several times. So just to tell you that it can be written in reasonably small space. And finally, I want to give a short introduction to the phase complexes, dendritic phase complexes. So it has in common with Marek Zawadowski's work that we deal with, well, the idea is to record all the faces, appearing in these pictures and their relation with each other, their subface relation. And the idea is that we will record when a subface is the target or when a subface is the source. So it means that we are dealing with graded posets, okay, because we, of course, going to subfaces decreases the dimension, and oriented in the sense that the subface, immediate subface relation is decorated, oriented, so with a plus or a minus information, okay? And then we have this magical axiom, which I learned from Ammar Hadzi Hasanovich in his works on diagrammatic sets. Yes, and this nice property of partial orders, which is called oriented, or of partial orders of this kind with orientation, this property called oriented thinness. Okay, so this property says that whenever you have like x, y, z in this situation here, so x, z and y are subfaces of each other, well, immediately subfaces, then it's always possible to fill this lozenge in a unique way with z prime. Okay, so there's a kind of mate to this little chain of two, well, this chain here, mate here, and with a nice property that the signs alpha 1, beta 1, so the plus and minus, are in this relation. Okay, and well, I don't have time to explain, but this condition, this very nice synthetic condition, actually explains quite well, or is explained quite well. It depends if you accept it or if you want to get to it, by the equations that I just gave. So inner globular and globular, the two globular equations and the inner equation correspond to situations like this. Okay, so again, I would need time to explain this, but let's And finally, what is a positive dendritic phase complex? Well, we add a few axioms. Well, actually, only a very simple one. So there is at least, because we are positive, there is at least one source. So delta is the set of sources of a term, and gamma is the set of targets of a term. Okay, the set of targets is just cardinal 1, and the set of sources is at least 1 because we are positive. Then the poset should have a maximum element. And finally, there is no cycle in the following relation, which we already saw. So you remember this, these triples. So in this language, these triples look like this. Okay, it says that Y2. Like this, okay? The target of Y3, which is written with this plus here, is the same as a certain source of Y2, okay? So we do not allow cycles for this relation, okay? And this end of this definition of positive dendritic phase complex, which is a quite compact definition. Okay, and finally, what we get is we didn't present the work in this way, but we could present it. We can turn around to show the equivalence between. So given a positive epiphyte, we can compute its successive targets and we will get a positive zoom complex. Given a positive zoom complex, we can actually collect all the edges of the successive trees in the zoom complex, and this will define our poset of faces. But of course, we will need to define exactly the poset, the subface relation appropriately, but the data are enough to define it. And finally, given a positive dendritic phase structure, while we can inductively associate epiphytes to all the codimension 1 faces of the maximum of the poset. And then it's also easy to see that these codimension 1 faces are organized as a tree precisely because of this no cycle condition. Okay, so now to summarize, we have 3 flavors. One which emphasize only sources, that's epiphytes. One that emphasize hereditary, targets, okay, that's zoom complexes, and dendritic phase complexes that are somehow agnostic, and they deal with both sources and targets. Okay, so now, because I'm essentially out of time, I will just give a very, very, like 1 or 2 minutes sketch of what needs to be done to lift this to the case of not being positive. So I will motivate this only through this picture, because otherwise I will explode the time and not give a chance for people to ask questions. So look at this picture. So this is we already know it from previous slides. So no, I'm not sure, because it's one. No, sorry. This is. No, we have seen it. So anyway, this picture is can be recorded in epiphyte style. Okay, so you can see here that the blue thing here has a tree structure, which is as usual, I would say, as before. But now, how can I describe, for example, the source in A1? Well, the source in A1 is something that has visibly 1 input here, 1 input here, 1 input here, and 1 input here. Okay, so it has 4 inputs. So it would be a tree with 4 nodes, like here, 1, 2, 3, 4. But you will probably agree that B3 and B4 are a bit special. Sorry, that B3 and B6 here, and B3, they are a bit special because they are loops. Okay, they are physically loops. So there is this idea of representing them as special nodes, which, well, in the Kock setting, they call them white nodes, okay? And so these B7 and B2 are black nodes, and these ones are white nodes. And the peculiarity of white nodes is that they are literally traversing an edge, in the sense that, well, it's just representing the idea that it's a loop, you know. B6 literally goes from C1 to C1. So this is nicely represented in this way. So, well, roughly speaking, in the world of general Opetopes, we are going to manipulate not only trees in the sense we had before, but also trees with subdivisions. So it's a word they use in the work of Kock, etc., which are trees like this with black and white nodes. Okay, and well, here's a technical definition. Also, a tree with subdivision is a tree whose some edges can be equipped with an additional information, which is actually a finite, finite total order. Okay, so here we have such a finite total order, here such one, and well, and it is convenient to represent them in this form. So now I will finish the talk with this. So we have to carry now information of this kind into the whole pictures. So for example, so I will skip this, but for example, now in designing the zoom complexes, in the picture, we also have these white nodes, and okay, so they are trees with subdivision that play a role in, well, in the final exact definition of Opetopes. And okay, these trees with subdivision make their appearance both in the zoom complexes and the epiphyte world, except that for zoom complexes, this is all clear and documented in Kock's paper, Kock et al.'s paper, while for the epiphyte case, this is, as we say in French, a travail en chantier, which means there is a lot to do. It's still under construction. And finally, something that is not in construction, but was also completely settled down by Louise, is the lifting from positive dendritic phase complexes to dendritic phase complexes. And she found out, and this is really her own work, she found out the way to sort of insert into the framework of dendritic phase complexes these loops by inserting a third. So now the covering relation, the subphase with immediate subphase relation, can be either positive, target, or yes, I'm finishing. Yes, sorry. So you can be either positive, okay, or negative, source or target, and then you have a third one, which is this zero, which means both being target and source at the same time, so to express loops. And she has very little additions to the axioms to make this work. Okay, so that's the end. I'm sorry because I took maximal not allowed time.
use the question time to get to that. Thank you very much. At the talk and the live stream. And I have to run, but if anybody would like to